So in today's lesson, we will describe about the matrix transformation. Also, we will discuss about the eigenvalues and the eigenvectors. So first of all, we will start from the matrix transformation. Basically, we know about the functions. As in the initial lessons, we saw that function is a rule that associates with each element of a set A1 and only one element in the set B. Now, here we will see that there is a transformation occurring when in the matrix system, and we call it a matrix transformation, which transform the values of a vector space Rn to the vector space Rm. For instance, here this is the important transformation about the vector spaces. For instance, like if V is a vector space and W is also another vector space, and F is a function or F is a mapping, which is a transformation from V to W. It takes the value from the one vector space V and transform the values to the another vector space W. And there is a special case when V is equal to W, then we call this transformation as a operator. Now remember that in this way we can also use the transformation in a way like if we take AX is equal to the B. For instance, here let me write some details regarding that one. Uh, So, for instance, we know that F is a mapping from vector space V to the vector space W. So, and it's take the elements of a defined as if we take any elements U from here, and we will get some elements W over here. If it's if we put V over here, we will get some W for V. This V they are coming from the vector space V, and this W is coming from the another vector space W. Now remember that if we apply this rule on a matrix, like if we have AX is equal to the B, so A is a metric, B is also a metric, and X is some vector. So AX is equal to B is a linear system. We have noticed that if we put some values of x over here and multiply with the metric v and metric a, so a times x it will comes a vector b. So this is also uh, performing in the same way as a mapping is performing the operation, and we call it a matrix transformation. Like here we have a transformation f from v to w. Similarly, this idea is also working whenever x is a vector or x is an unknown. When we apply or multiply this one with some b, some a metric, then ax is equal to b, where b is the output or b is like behaving in this way. Now notice that if these are the vectors, so f is taking the elements of a v, like since v is a vector space, so it have element x1 x2 up to xn, and for each element whenever it's apply on that we will get some w1. Similarly, f2 will give us w2 and up to so on fm, its m tuple will give us wm. So, and if we combine all these, we will get a unique element or a unique vector in Rm, which is W1, W2 up to Wm. So it means that we can combine this and we can say there is F1, F2, F3 as a T, and T is a transformation from Rn to Rm. So this is will gives us the idea of a matrix transformation. For instance, we can see that if W1 is equal to A1 x1 plus A2 x2, A1 A11 x1 plus A12 x2 plus up to A1 n xn. Similarly, W2 is in this form. So we can take x1, x2 as a common from that and write as a matrix notation. So when we write this in a matrix notation in this form, then we call it the right hand side as the left hand side, we say it's a W is equal to AX. So this is the same way like as we write as AX equal to the B, or uh, B is equal to AX, or similarly we can say that W is equal to AX. So this is called a matrix transformation, and this transformation is very important and simple because later on we will see that every matrix transformation give us a linear operator. we can get this as this A. If you notice that A is a given metric, when it's applied on any x1, x2 up to xn, any vector, then it will give us some resultant or some output. This output will be the w1, w2, wn. So it means matrix multiplication with a vector is behaving like a function or behaving like a mapping. So this is called a transformation that maps the column vector x in Rn into the column vector w in the another vector space Rm. So this is the idea. So it means that when and we just call it like this A is a metric. So if we call this A as a operator, or this A we call it's a matrix transformation, then it means it takes the element of a x and moves to the another space which is w, a vector of Rm. So it means that TA is a matrix. It takes the vector from the vector space Rn, and it moves to the vectors in W, where W is coming from Rm. So this is called a TA is a map X into W. So this is, we call it a matrix transformation. And here we can see that there are several examples of this transformation. For instance, if T is a transformation from R4 to R3 defined in this way. Like we just put x1, x2, x3, x4 from the four dimension space R4, and we will get W1, W2, W3. These, if we combine W1, W2, W3, they are vectors in R3. And we can express simply this in a matrix form, like if we combine W1, W2, W3 in the left side, and in the center we can take the coefficients like 2, -3, 1, and -5 and combine them. So it will give us a metric. And on the other side, if we put as a x1, x2, x3, x4, and notice that if we multiply this again, then it will again will become its equilius form. So it means we can write into the matrix form. And you have to notice that here you can get a metric A. So this metric A is very important, and we call this as a standard metric for T. And this metric A is is playing as a operator. Like it's take the element x1, x2, x3, 4, x1, x2, x3, and x4, and it when it's multiplied with the A, it will gives us a new vector w1, w2, w3. It means this matrix is playing a role of a matrix transformation. So it's playing like a function. For instance, if we put some vector of a R4, for instance, like 1, -3, 0, 2 over here, then you will, if you multiply with the metric A, then you will get output as a 1, 3, and 8. It means that it gives us the elements in W. So, so it will gives us the elements in R3. So it's take the elements from R4, and when multiply with the metric A, it gives us the element in R3. So this is called a matrix transformation. One thing is very important, that in these matrix transformation, there is always a standard metric. So this standard metric we can simply get, and this metric have a variety of important features. Like this, later on we will see that this transformation will always gives us a linear transformation, which is the very important tool of a linear algebra. Now we can see that like since behind the linear transformation there is a matrix transformation, and when it's a matrix transformation is it has some useful properties uh, that are also called the property of a linear operator. For instance, the first property is that if you put zero vector in that, so a0 is always equal to the zero, where the first zero is coming from Rn and the second zero is coming from Rm. Here you can notice that what happened if a is any metric. If you multiply the zero here, zero column, like x1 is 0, x2 is 0, x3 is 0, and x4 is 0, and multiply with the A, then simply we will get W1, W2, W3 as a 0, 0, 0. It means the linear transformation always give us the output 0 when the domain element is 0. And moreover, if you take a k u, then answer will be k times t a u. Like the k can be take as a common, and this is called the homogeneous property of a this operator. And furthermore, t of u plus v, like t of u plus v means a of u plus v is same as a u plus av. So this is the additive property, or you can see that it's a distribution. And similarly, t of u minus v is equal to t of u minus t of v. These are the useful properties they are taking from this. So it means whenever x is a vector in Rn, and when you apply t over here, it moves this one to another space, and that is called the like this can be same. When it will same, then it we call its operator. And when m and n are not same, then it means it's called a transformation. So it means t is transform the vectors from of Rn to the vector of Rm. Uh, so this is these are the results regarding that one. And if here we can also see that if t is a transformation from Rn to Rm, Ta, and also Tb is a transformation from Rn to Rm. So these are the two matrix transformation. And suppose that both are equal. If both are equal, then it means behind or inside the matrix are also the same. Like if Ax equal to the b, then T of A is equal to T of B. Like for the both entities, they must have a same and unique metric. There are some examples of this transformation. The first transformation is a zero transformation. Like if you take a T as a zero matrix, so with the zero metric, whatever you multiply the vector, the answer will be always zero. And we call it a zero transformation. And another interesting transformation is identity transformation. Identity means identity metric. If you take identity metric and multiply with any vector, again you will get the same vector. So it's called identity transformation Ti, denoted with Ti. And then there are some examples of that transformation, and we can also get its standard form. For instance, if we have a reflection about y-axis, T of xy is operator from R2 to the R2, because it's taking the element from R2 and also giving us the elements in R2. So you have noticed that it just put x as a minus x comma y. So how we can get its entries? Just if we apply the standard elements like E1, which is the basis of R2, and E2 is also the basis element of R2. Whenever we apply there, we can get its answers, which is like minus 1, 0, and 0, 1. So it means you can just write into the matrix form. So it means standard matrix of this operator T is minus 1, 0, and 0, 1. So here there are the many ways for which we can get the standard matrix. But remember that all these matrix transformation, there is a standard matrix which we can simply get from that. And remember that from that metric, if you multiply with x and y, you will get again the same vector minus x comma y. So it means behind the standard metric, there is a behind this matrix transformation, there is a standard matrix which we can simply attain. But these have some useful properties. There are many useful features of that transformation, and these are very useful, which we can see in the later lessons. So these are all the examples of a, matrix transformation, and we can simply get the matrix operator for that. So these are the operators, and standard matrix are there. So simply what you can do is you can just put E1, E2, E3, which are the standard bases of R3. You put over here in the T, and simply you can get the vectors, and whenever you combine that vector, it gives you a metric, and that metric is called a standard metric of the operator T. And also there are some rotation. We can use it whenever we apply the cos theta minus sine theta and sine theta cos theta. So this will also give us some sort of a rotation and rotation equations for Rn. For example, if we want to rotate with the vectors with some angle theta, so what we will do is that like just take this form of a transformation. which state that cos theta minus sine theta cos theta, if you multiply with any vector x and y, then you will get its resultant value w1 and w2. So this will gives you a rotation of equation. For instance, if you take x over here and with some angle theta, whenever you apply some value of a theta, then it will give us W1 and W2 on the another place. So this is the example of a this operator which have rotation through the angle theta. So these are the transformations, and these transformations have some useful features which we will describe its useful results in the later lessons. But these are also examples of this one. Like there are some important form of its transformation or operators. One is called contraction. Contraction mean if you take t of xy is equal to kx ky, where k is strictly less than 1, then what it will do is that, so if you have a vector from 0 to x, like it's x comma y, then whenever k is strictly less than 1, so it will gives us kx comma ky. The vector will be shrink from that one. Similarly, if the dilation with factor k on r square when k is strictly greater than 1, then it's increase the length of that vector of this. You can see that contraction mean it's contract and it's make them into the smaller form. And the other thing is that if you take the k value as strictly greater than 1, then it will increase its inside the area of that one. So standard metric of a these two operator is k0 0k. So it means any vector xy, when you multiply with k0 0k, then it will gives you this type of a operators, this we call it say contraction and dilation operators. And similarly in K3 we can see the examples of these ones. And there are the many important features in the physics and in the mathematics. For examples, the rotations, rolling pitch, and the rotation of a these elements can be controlled by these types of a linear transformations and or the linear operators. So these are the examples, and hopefully you can see that how we can get its the other form. For instance, if a1 is equal to this one, so we can define the standard operator for that. Whenever you multiply with x comma y with a1, then it will gives you some of its form, like it will becomes like x plus 2y and comma y, because the second element is 0. So it's just like a matrix multiplication with some vector. And so these are some sort of examples regarding that one. And when we come up to some of its properties, and whenever we see its compositions means when we have the two operators, one is the TA and the other is TB, then the composition of two operator is also an operator. Similarly, the composition of a two transformation is a transformation. For example, here you can see that if TA is an operator from Rn to Rk, which takes the element x and moves to the Rk, then TB is operator from Rk to the Rm. Then if their composition we put like this: TBOTA is a composition. It's take directly element from Rn to Rm, and we write this TBOTA. Like first apply the TA and then TB. Like we know that if you have the operator's equation, so first we need to apply TA on the vector, then of its output, again we apply the TB on that. So it will gives us element from this is a mapping from X to the from Rn to the Rm. So this is called the composition or a composition of a matrix transformation. Here we can see that its standard form, or it's a more general form, like if TA is operator, or it's a TA is a transformation from Rn to Rk, TB is a transformation from Rk to RL, and TEC is a transformation from RL to RM. Then its composition like TC or TB or TA, it's a transformation from RN to Rm. So it moves elements from one vector space to the other vector space. So here we can see that how it will comes. So it's just simply multiplication of that, like T2 times TA is the multiplication of these matrix of its form. So we just need to multiply that. The composition is simple, but this composition is not always commutative. Like we know that behind the matrix transformation, there is a there is a metric A, and in a matrix A metric multiplied by B metric is not always equal to the B metric multiplied by A metric. It means that AB is not equal to BA. Similarly, here we have a result that T1 or T1 or T2 is not equal to T2 or T1. Like because here you can see that if T1 is a have a standard metric, the first one T2 have a standard metric, the second one if you multiply, then T1 or T2 is 0, 1, 0, 0, and T2 or T1 is the metric where in the when T2 is coming first and T1 is coming second, in their product it will give us 0, 0, 1, 0. So notice that T1 or T2 is not the same as T2 or T1. So, but this will always gives us a composition of that one, and also it have some features that we can use it for the inverse of that one. So we will see these features later on about that. So, these are the some results regarding the matrix transformation. But here there are some useful results. Like if A is a metric, A is an n cross n metric, and T is a operator, metric operator from Rn to Rm. Then the followings are equivalent. Like if A is invertible metric, invertible mean A inverse exists. Then the range of TA is Rn. It means the range of A is covering the whole vector space Rn. It is equal to the codomain of the range of T is equal to the codomain of TA. And T is also 1, 1. 1, 1 mean it gives us a single output of each value of Rn. So you will get a unique value in Rn. So this is a 1 1 operator. So 1 1 is same as we saw for the functions. So these are, and when it's a 1 1 function, then inverse of this is also exist. Like we can get T inverse of A. So we will also see later on about that one, that how one can compute the inverse of these transformations. But these are some introductory about that these transformations, and here you can see that if T is 1 1 operator, then T inverse is exist, and T inverse take the metric and it moves elements back from Rn to Rn. Like from if T is a mapping from A to B, then T inverse is a mapping from B to A, like it's reverse the elements in the other form. And also remember that the T of A times T inverse of A gives us identity metric. Like we know that A times A inverse is identity, A inverse A is also identity. So here this is a matrix transformation. TA is a metric, TA inverse is also a metric. So it again, if TA is a mapping from X to W, then T inverse of A is a mapping from W to X. It's just reversing back the elements of that. And here, if we know the metric A, then we can find A inverse by simple rule. So the answer, the thing is same. Like if A is a metric, then we just find A inverse. So as A is TA, then A inverse is TA inverse. Here you can see that T A inverse is same as TA inverse. So these two things are the same thing. And we just need to find the inverse of that one, which is very easy. Here, this example tells us that how to find the A inverse. For example, if T is a mapping from R2 to the R2, defined in this way that W1 is equal to the 2x1 plus x2, w2 is equal to 3x1 plus 4x2, and it's given that it's 1, 1. Then find T inverse of W1, W2. What is the inverse of that metric? So we know that here we can write this into the matrix form. We can express this in a matrix form, because behind this transformation there is a there is a standard metric. So if you get this standard metric, you call it a T metric or A metric. Then find its inverse. We know that how to find the inverse of a metric. There are many rules. We can find inverse by elementary row operation, or we can find inverse by the inverse method, or there are several other methods for available to find the inverse. Adjoint method is also available. So when you find its inverse, so this inverse is actually the inverse, or it's denoted with T inverse. So and remember that when you multiply T inverse with the element W1, W2, it gives us give us an element in the, again, back to the first space. So you can check that, like if you put any element x1, x2 over here, it will gives you the answer in some feature space, or in the range set. And when T inverse apply on the range set, so it will gives you the domain element of T. Like here we can verify that. So if we know the what is the operator T, we can also find T inverse of that metric. So this example is very important, and you need to see about that. And look, these are again the operations are available that one, and these operations are very, very important, because these two operations tell us there's that every matrix transformation is a linear transformation, because if you put T of u plus v, the answer is always equal to T of u plus T of v. It will split, and this additive property will become split into the two parts. And T of ku is equal to k times Tu, where k is any scalar, either positive, negative, or zero. So these are the two important features of this metric operator or matrix transformation. So here every linear transformation from Rn to Rm is a matrix transformation, and conversely every matrix transformation from Rn to Rm is a linear transformation. So it means matrix transformation and linear transformations are one of the same thing. And there is some equivalence result that if A is invertible, if like T is a operator from Rn to Rm, or Rn to Rn, and if you know that behind linear transformation there is a metric A, and if A is invertible, then it means Tx equal to 0 has a only zero solution, which is called trivial solution. And whenever you reduce A as a echelon form, then you will always get the identity metric In. A can also be expressed as a product of elementary matrix. Ax equal to b is consistent, and it has a unique solution for every value of a b. And Ax equal to b has exactly one solution, and determinant of A will be non-zero. So these all statements will be equivalent in that case. And moreover, they have also some useful properties, like you can see that columns of A are linearly independent, vectors of A's are independent, and columns can span the whole Rn, and rows also can span the whole vector space Rn, and nullity of A is 0, and the rank of A is Rn. So since all rows will be non-zeros, because it's identity metric form, and then it means its rank is n. And so these are the some useful properties. And when you will take the operator ta, so its range is Rn, and moreover ta is 1, 1. So this operator will always be a 1, 1 operator. So these are about that one. So if you will see about some questions regarding the assignment problems, like if T is operator from R3 to R3, and T2 is also operator from R3 to R3 defined in this way, then find the standard metric of for T1 and T2. So it's not a difficult. For example, we know that what are the standard bases of R3. If you put 1, 0, 0, then you will get first vector or first row of a standard metric T1. When you will put 0, 1, 0, then you will get the second row of a metric. Similarly, 0, 0, 1 gives you the third row of a metric. So when you combine it, then you will get the standard matrix of T1. Similarly, if you put E1, E2, E3, then you will get the first row, second row, and third row of a standard matrix of T2. And similarly, find the standard matrix of T1 or T2. So T1 or T2, like if you have a metric T1 and T2, then you can multiply that, because T1 or T2 means just you multiply the first metric with the second metric as you obtain from the part A, then their product will giving you their product of two matrices is giving you T1 or T2, and similarly to T2 or T1. Remember that as we know that A multiplied by the two matrix product, like A metric multiplied by B metric is not always equal to B metric multiplied by A metric. It similarly we have A1 T1 or T2 is not always equal to T2 or T1. And remember, when you multiply the metric A with T1 metric with T2, then write T1 first and T2 second, because if you interchange them, then it will make a problem because they are not always commuting or commute. We know that 1 multiplied by 2 is same as 2 multiplied by 1, but this commutation is not hold in the matrix. And also need to find the formulas for a T1 or T2 of that one. So when you have a standard metric, when you multiply with x1, x2, x3 of that, so you can simply get its formula. Like here from the part B, you can get a metric and metric multiply with a vector, column vector x1, x2, x3. In the both cases, you will get the two formulas. And then there is a next problem is find the standard metric of the operator defined by this, and to check that this operator is 1 1 or not. So there are many ways to check the 1 1 or the standard metric. We know that if we write the its standard forms like 1 1 minus 2, 1 minus 3, and 1, similarly 1 0 minus 2, so that is the standard metric. You call it a metric T. The second thing is that check that it's a 1 1 or not. 1 1 mean is the metric A is it's invertible. Like just take its determinant. If the determinant is non-zero, then it's mean this metric is 1 1, because there is a result that this operator T is 1 1 if and only if the metric A is invertible. So just take its uh, determinant. If determinant is non-zero, then it means this operator T is 1 1. This is the simple technique to obtain that. The next thing is about the eigenvalues and eigenvectors, which is also the interesting part of that. Uh, if you have any question, then you can ask now, or you can ask your question later on when we complete the second topic, which is related to the eigenvalues and eigenvectors along with the characteristic polynomial. Now here we can see some result about the eigenvalues and eigenvectors. So this is the another important characteristics of a linear algebra, which is gives us a metric theory, because you know the linear algebra mean matrix theory, because matrix have a beautiful features. So if A is a metric n cross n, then non-zero vector x is called eigenvector of A if and only if AX is the scalar multiple of x, that is AX is equal to lambda x. Look, x is some non-zero vector, A is a metric, and lambda is the some scalar. So if you note this thing, A is a metric, A multiply with x. This is some kind of a transformation, and lambda multiplied by x is a lambda is a constant multiple with some vector x. So it means the lambda is playing the same role as A multiplied by x. A is a metric. So metric multiplication with vector is a vector, and scalar multiplication with the vector is also a vector. If they are the same, then this means that this lambda has the same characteristics, same features that have the metric A. So it means lambda, this lambda is called the eigenvalue of metric A. And all those x which satisfies this equation that ax equal to lambda x, that x are said to be the eigenvector corresponding to the given lambda, because there can be more than one lambda which satisfies this condition. So now let us see about this one, that how we can deal this with the values of a lambdas. So these lambdas are very important. For example, we can see that how this lambda we can get. And there is a eigenvector of 2 cross 2 metric. For instance, if we have a x is 1 comma 2 and a is a metric like 308 minus 1. Now the corresponding eigenvalue of eigenvalue is lambda equal to 3. We can check that how does this value we can get, because this 3 is the diagonal entry, but all the diagonal entries are not always the eigenvalue. So what we will do is that we can check that is this 3 eigenvalue or not. Like if a multiply by this x is available over here, so you will get 3 times 3 6, and if you take 3 common, then it will becomes 3x. It means for this eigenvector 1 comma 2, the lambda is eigenvalue because ax is playing as a 3x. So it means this 3 plays the same role as this metric is. So it means this constant have ability to get all the features as the matrix A is. So this is called the eigenvalues and eigenvector. So lambda is called the eigenvalue and the x is called the eigenvector. So we can find the eigenvalue with the help of some equation which is called the characteristic equation. For instance, we know that if ax equal to the lambda x, so the we can take ax on the other side or lambda x on the other side. The rest of side will becomes a zero. This zero is a zero vector. Remember that, because ax is a vector, lambda x is also a vector. So you can subtract the first from the other. With when it comes to the other side, then there will be minus sign, and the right hand side you can get a zero vector. Now, this we can find its eigenvalues whenever uh, we take its determinant. And suppose that if A is the n cross n metric, then lambda is the eigenvalue of A if and only if it satisfies the equation that determinant of lambda I minus A is equal to the 0. And this is called the characteristic polynomial. Sometimes we denote with the p lambda this equation. For instance, here we can check that how to find the eigenvalue. So if you have a metric A, then just take determinant of lambda I minus A. I mean identity metric. So you just need to write identity metric from that. So and subtract A from that and take its determinant equal to the 0. Determinant is always a real number. When you multiply that, you will get an equation, and the roots of that equations are the eigenvalues. So here, since it's a 2 cross 2 matrix, so it means it has at most two eigenvalues. The first one is 3, the second is minus 1. Sometimes the eigenvalues are the diagonal entries, but not always, because for there are many cases for which the eigenvalues are not the diagonal entries, but there is a one relation that the sum of eigenvalues is always equal to the sum of diagonal entries. And you know that the sum of diagonal entries we also call the trace of a metric A. Trace means the sum of diagonal entries. So you can check that is here the trace is minus 2, like 3 plus minus 1, which is equal to the plus 2. So plus 2, and similarly the sum of eigenvalue is also plus 2. Here we can check that sum of eigenvalues is always equal to the trace of a metric. So here, for example, since we have a 3 cross 3 metric, A is a metric, so we can find its eigenvalues by this characteristic polynomial. Just take determinant of lambda I minus A, which is the determinant of a of this lambda I minus a. So it will give us a characteristic polynomial, and you just need to find the roots of that one. So there are many ways to find the roots of this polynomial, which you already studied in your previous classes. So when you find its root, then the roots will gives you the eigen values. So you can check that these are the three values. What is the sum? If you make the sum of all these three values, so it will becomes 4 plus 2 minus under root 3 and plus 2 minus 2 plus under root 3 and 2 minus under root 3. It will gives you 4 plus 2 plus 2, which is 8. And if you check the trace means the sum of eigenvalues. Sum of the diagonal entries. 0 plus 0 plus 8 is also the 8. So it means you can verify that sum of eigenvalue is always equal to the sum of diagonal entries. But here, if you have an identity metric, then the eigenvalues of a identity metric is always the diagonal entries. Similarly, if you have a upper triangular metric or lower triangular metric for which upper entries are existing and lower entries are 0, or the lower entries existing and upper entries are 0, in that case, again the eigenvalues are only the diagonal entries. So you can see that there is a result which shows that these diagonal entries are the eigenvalues. But if you have a metric which is not upper or lower triangular metric, then the eigenvalues can be different, which is not always the its diagonal entries. So as we saw that eigenvalue is the solution of lambda I minus ax equal to the 0, which is again, if you see, it's a homogeneous system. And we remember that solution of a homogeneous system is a vector space. Is a Solution is always of homogeneous system. We call also it's a null space. So here we can, if this is a null space, we can find its basis, and that basis is called the basis for eigenspace. So these we can get eigenvectors, and these eigenvectors are also called the basis of a eigenspace. So for example, if you have a metric, find the basis of a eigenspace, like if we have a metric A, so we know that from the characteristic polynomial, like determinant of lambda I minus a is equal to 0, if we take that, and from this, we can get its two root, and these are called the eigenvalues, like 3 and minus 1. So if we have a eigenvalues, we can find eigenvectors, means those vectors which satisfies this equation that lambda I minus ax is equal to the 0, means which for what class is satisfying this relation. So all those x will makes a one vector space. This is called the eigenspace, and that eigenspace have some basis, and that basis we call is a eigenvector, and that eigenvector is also called the eigenvector corresponding to the given eigenvalue lambda. For example, as you see that 3 is the first eigenvector. So if you put 3 over here, and then this system will becomes in this form. Then from this homogeneous system, we just solve it. Then there are two possibilities. One is we can get only the trivial solution, and the second is we can get a non-trivial solution. So if you get its trivial solution, then still the vector, the value of x1 x2 is the vector which is the eigenvector corresponding to lambda equal to 3. And if it have a non-trivial solution, then still we can get its eigenvector. For example, you can see that it has a parametric solution. So from this parameter tt, if you just take t as a separable of the form, then it means this is the vector 1 to 1. So it means this is the vector x that satisfies this condition that ax equal to the lambda x. So we call it the corresponding eigenvector to the lambda equal to 3. Similarly, we can find the eigenvector for lambda is equal to minus 1. So just you put the value of lambda equal to minus 1 over here, and then solve it. Then you can get a vector. That vector is called the eigenvector corresponding to the lambda equal to minus 1. And this we can also use for and like there are variety of applications of these eigenvalues and eigenvectors. So it can be solved linear systems. It have the many other features, and many useful results are based on the eigenvalues and eigenvectors. So if there is a 3 cross 3 metric, then we can just also get the characteristic polynomial by taking the determinant of a lambda I minus a is equal to 0. So when you take a determinant of lambda I minus a equal to 0, you will get characteristic polynomial. And after finding its root, you can get the eigenvalues, which are 1, 2, and again 2. Because 2 has a square, its degree is 2. It means if polynomial have a degree 2, it means the roots are repeated. So you can check that the eigenvalues are 1, 2, and again 2. So if you make it sum, 1 plus 2 is 5, and the sum of diagonal entries is also equal to 5, like 0 plus 2 plus 3 is 5. So this relation we can also verify it. Now what happened is that we can find its corresponding eigenvectors. Like if we, in case lambda is equal to 2, just put the lambda equal to 2 over there. Then if you put over here, then it will gives you this form of a homogeneous solution, a homogeneous system. Then by applying the Gaussian method or any method, we can get its solution. Like here you can see that it's a parametric solution, we can get it. And with the parametric, if you take its component as a common, then it means that there are two vectors. So these vectors are called the eigenvectors of a lambda equal to 2, corresponding to lambda equal to 2. And remember that they both are independent, because s and t's are independent to each other. They are the two different of that one. And with this combination, if you see that this solution x is a itself gives us a solution space of that one, which is a which we call a null space, because solution of a homogeneous system is always a vector space. Now, similarly for lambda equal to 1, just put lambda equal to the value of lambda equal to 1 in this system, and it will again gives you one kind of a homogeneous system. When you solve it, you can get some of its solution, and when you take S common, so you will get the basis of that one. So this basis is called the eigenspace corresponding to the lambda. So this is the method to find the eigenvalues and eigenvectors of that one. And here there are some useful results that for regarding this. Like if you have a k is a positive uh, integer, lambda is the eigenvalue of a, and x is the a corresponding eigenvector, then lambda k is the eigenvalue of ak. Like if lambda is the eigenvalue of lambda is the eigenvalue of a, then lambda power k is the eigenvalue of a power k. So this is a very useful result, and this can also gives us the eigenvalues of a any power of a. For example, if a is a metric and we know its eigenvalues, then for a power 7, we can find its eigenvalues. Like just take the power 7 of that one. So like 2 power 7 is 128, which is the eigenvalue of a power 7. And similarly, the second lambda power 1, if you take its power 7, it's again 1 power 7 is 1. So it means second eigenvalue is 1. So this is the result regarding that one. So we can compute and see this relation. Similarly, there is a one thing that if A is invertible metric, if and only if lambda is not equal to the 0 as the eigenvalue of a metric A. So if lambda is not equal to 0, it means this have a eigenvalue for which we can where which shows that if lambda is not 0, then it means this metric A is invertible. And these are some important relations regarding that one, that if A is invertible, then Ax equal to 0 has a trivial solution. You can reduce it into the echelon form as a IN identity metric. And so here, nullity plus rank, we have already see before. This lambda is equal to 0 is not the eigenvalue of A. So these are just recalling all the previous summaries of that. So these all results are related to the each other. And here I also mentioned some of results for you, which may be helpful for you, like and its proof. For instance, if we see this result, Like if lambda is the eigenvalue of A, then lambda square is the eigenvalue of A square. So here you can see it's simple proof that since lambda is the eigenvalue of A, then it means Ax equal to lambda x. It always satisfies this relation. Now, if you multiply A on the both sides on the left side, so A multiply over here and A multiply over here, so we can write it's A times A, and here we know that lambda can be take common from the matrix inside of the matrix. So lambda will becomes outside and A times A will becomes A square x. So it means A square is equal to the lambda times lambda x. We know that here we have Ax, but it is given that lambda is the eigenvalue. It means Ax equal to lambda x. So instead of Ax, we can again write lambda x. And we know that lambda times lambda is equal to lambda square. It means A square x is equal to lambda square x. So if this is the relation, this is the definition of a eigenvalue, that if A square x equal to the lambda square x, it means that this lambda square is the eigenvalue of A square. Here there is another result that if A is invertible, like inverse of A exists, and lambda is not equal to the 0, is the eigenvalue of A, then 1 over lambda is the eigenvalue of A inverse. We can see that since lambda is the eigenvalue of A, it means it must satisfy Ax equal to lambda x. Now, if we multiply A inverse on the left side of the both sides, so A inverse will be multiplied on the both, so A inverse comes over here. So here we see that lambda can be take common from the matrix multiplication, and we know that A times A inverse is identity because A is invertible matrix. Here just put I because A times A inverse is identity. And we know that here if we take the lambda common from that, so it will becomes A inverse X. And remember, lambda is non-zero. It means we can divide the lambda on the other side. So or just multiply 1 over lambda on the both sides. So Ix equal to the simply X. And here if lambda comes to the other side, it will becomes 1 over lambda x equal to A inverse x. Now, if we interchange this like A inverse x equal to 1 over lambda x, it fulfills the definition that this 1 over lambda is the eigenvalue of A inverse. So this is the simple proof of that one. Here, we can also find the eigenvalues. There are some examples for you which are available over here. For instance, that if T is a linear transform, T is an operator, is that form. So find the eigenvalue of this. So we know that behind the linear transformation, there is a standard metric. So we can just take the standard metric Ax is equal to the B. B is on the other side like this one. So what we can do is that just find the eigenvalue of this. So if lambda is the eigenvalue, then it will satisfy Ax equal to lambda x. So just take that relation, and you know that we can subtract minus lambda on the other side. When it comes to the other side, then the right hand side will become 0. And we can take one x comma y common from that. So it will becomes like if you take a common from that, so there is an identity metric come over here. So it means that it will be the a minus lambda I x is equal to 0. So if you subtract that one, 0 minus lambda and 0, 1 minus 0 is over here, minus 2 with 0, and also minus 3 minus lambda times xy equal to 0. So this is a homogeneous system. How to find the lambda? Just take to find the solution of a characteristic polynomial, which is lambda I minus 0. Or you just can say a minus lambda I, a lambda I minus 0. So it will gives you the characteristic polynomial. Just take the determinant of that one and determinant of this one equal to 0 and solve it for its roots. When you solve it, you will get the value of lambda I with the first root and the second root. It means these two are the eigenvalues of a this linear operator T. Similarly, if we have a 3 cross 3 matrix, we can find its eigen vectors. Like if we the eigenvalues are available, we know that it's a upper triangular matrix, then it means 258 is the eigenvalue of that. So we can find the corresponding eigenvectors. For instance, if you put lambda equal to 2 over here in its characteristic polynomial and solve it to find its root, so you can get its corresponding eigenvector. So for lambda equal to 2, we can get the corresponding eigenvector as a 1, 0, 0. So remember that this is the eigenspace because it's give a complete vector space, and this eigenvector is also the basis of a this eigenspace. Similarly, for lambda is equal to 8, we can put lambda value 8 and solve it to get the corresponding eigenvector. So this is the corresponding eigenvector we can attain for this case. And there are also some other examples which I will also upload for you. So find the eigenvalues and eigenvectors of this operator. Here you can get the standard metric A. Standard metric for T is this metric, which you just can get it's the entries of that in a column in a row forms, and just solve ax equal to lambda x. Then it will gives you the characteristic polynomial, and the solution of this characteristic polynomial will is actually the is equal to this and take its determinant. When you take its determinant, then determinant of a take determinant of this one, and it will gives you the two roots. Sometimes the eigenvalues can be real and sometimes it will can be complex, because you know the roots of a polynomial can be real or complex. If it's complex, then still we can find that entries. And for the there is a one example that what happened when the values of lambda i's are complex, and also to find the eigenvectors of this. Here the complete solution of lambda, the complex values are available, so you can use the elementary operation to get its solutions. So one of that example is available over here, that how to get the lambda i's for this. So this is the example, and here there is a one interesting result, that if we know that determinant, the characteristic polynomial is actually equal to the is the determinant of a lambda I minus a, which is the normally a naught lambda power n plus a n minus 1 lambda power n minus 1 plus up to a naught. So this is the characteristic polynomial. If we put the if we put lambda equal to 0 over here, then what will it becomes? It will becomes determinant of minus a is equal to a naught. It means the determinant of minus a is a naught. And we know the determinant of minus a is the minus times, like here I just need to add one more step. Like we know that determinant of, if you take the minus common from here, so the minus will becomes outside. This is the property of a determinant. And if you multiply the minus on the other side, then it means determinant of a is a naught. So this is the result regarding that one. And now if we see some examples for that, so this, I think the problem number 23 is to find the determinant of a metric A whose characteristic polynomial is lambda power q plus 4 lambda square minus 3 lambda minus 5. So here you can find its solution by this result, that determinant, we know the characteristic polynomial is determinant of lambda I minus a. Now what is the way that if you put lambda is equal to 0, then it means it will, you know, the lambda is, if lambda is 0, 0 multiplied by any metric is 0 metric. So 0 minus a is minus a, and it is equal to the last coefficient, as you can see the last coefficients of your result. And if you put the minus, take common from that, from determinant, because this is a property of a determinant, and you can put the minus on the other side. It means determinant of a is only the constant minus of minus a naught, the coefficient of that. So this result will be helpful to find the solution of a problem number 3. And also the next problem, to find a power n if n is any positive integer. A is a metric over here. So we know that how to find the a square a cube up to an. So this you just need to write a general form of that. So there are many ways to obtaining the result regarding this one. And but here you just see that what is the an, or what is a exact form of an. So the an mean a power n. So this you mean, like, a square is a multiplied by a cube is a square multiplied by a. So this is the problem regarding this. So now if you have any question, you can ask your question. Yes, please. Yes, you can ask your question. Yes, please. First unmute, then you.
For the I think it's the first question for the assignment. There's a part where you have to use what is it, composition of the matrix. The first question.
Which question?
Yeah, no, the number C. Use the matrix obtained. When they say we have to like do the composition, should we substitute the x1, x2, x3 inside the other value or times them? I don't know if it makes sense.
There is some interruption in your sound. Can you please repeat your question? And which question you are asking?
Third question, problem 21C.
Okay, yes.
Yeah.
So in 21C, from the first part, you will get a metric. Like in the first part, you know what is the TA. T is the first metric, T2 is the second metric, which you can simply obtain from here. Now, if you multiply the T1 with T2, then it will give you standard metric of T1 multiplied by T2. Similarly, from the first part T2 is available, T1 is available. If you multiply these two metrics, you will get T2 or T1. When you have that metric, so just multiply this metric as a with x1, x2, x3, then it will gives you the first formula for T1 or T2. And similarly, T2 or T1, when you multiply x1, x2, x3 with this metric T2 or T1. So then you will get this of its form.
Oh, so we don't have to like let's say 3x1, we substitute it into x1 minus x2. We shouldn't do that.
Uh, okay. Wait a second. Let me make some example for you regarding that one. So example. So here, let's see the one of that one. Suppose, here, if you have a one operator, say T1 is an operator, so it moves, it say like X, Y, Z we have, and suppose there are some of its forms, say X plus Y, the second component is Y minus Z, and the second is say like X plus 2Z. So this is the first operator. And the second is say like x2. Suppose it is another operator, so x minus 1. Here maybe only the 2y, and here we have here like let me make some changes. So here there's some z, and here it's suppose the 3x plus y. So these are the two operators. Then the question arising that how to find. First thing is find find matrix, find the standard matrix for say T1 and T2. So look, there are many ways to find the standard matrix. So one is that one, if you put the entries like identity matrix 100, 010, and 001. The another thing is that you can get the simple entries over here. I'm just writing the directly of that in the first part. So how to find, like I have a since this is a 3 cross 3 matrix, so I just put the entries of a 3 cross 3 matrix over here. For instance, here, let me take the 3 rows and 3 columns over here. And remember that here x is what? The x is 1, so it means x values is giving you 1. The y is also giving us 1. Uh, and the another approach is that if you put the e over like 100 over here, if you put 100, so you can get its values over here. So when it's 100, then it means you will get the entries regarding this. So as in the first entry, you know that there is a 1x, so x is coming over here. In the second entry, there is no x, so it means there is a 0. And the third is the z value is the x is over also over here, so it will becomes 1. So it's also the image of 100, because 100 is the first vector uh, of a basis set of R3, which is 100. Now you put 010. If you put 010 over here, then it will give you some entries like 1, 1, and 0. And if I put 001, then it will gives us the 0, -1, and the 2. So this is the standard metric of TA. And now to find the standard metric of a T2 from the second one. So here again we need to obtain its result by applying this operator. So if you put E1, which is 100, then it will be 103, the first row. Secondly, need to put the 010, which gives us a -1, -1, 2, and 1. And last put 001. Then if you put 001 over here, then it will gives us 0, 0, 0, because there is no z over here. And you can check it like if you multiply here, I just say verify for you that if you multiply this with any x, y, z, will it will come the same answer as this one or not in a column form? Like you can check that if you multiply this one, the first with the second into its column form, then will it gives you the same answer for that or not? So this is the verification of this one, and from this verification, or from this of its transposition, we can get its standard entries. Now when you have this metric, the next thing is as asking that find the standard matrix of T1 T2. So for T1 T2, what you need is that you just multiply T1 with T2, because these are the matrix, so you will get its product of that. And again, when you put the vector xy over that, then it will gives you the form of T1 or T2 and T2 or T1 in this way. So this is the method to get the entries for this one. Okay, like T1 or T2 and T2 or T1. So as these are available in this form, similarly we can get its the second form.
Also, so we just multiply the two matrices,
Yes, yes. Because
or
if you see
even
over here, so it's a matrix, two matrix multiplication. Like here it is also, if you will go through from that, look, T1 or T2 is the product of two metric. Like if T1 is a one metric, T2 is a second metric, so their product is the product of two metric. Just similarly to T2 or T1 is the product of T2 multiply T1. And they are
okay,
showing
so
that
so
T1 or
so
T2
for
is not equal to T2 or T1, because the numbers are commuting. Real numbers are commuting, but metrics are not commuting. So T1 or T2 is the just a product of that one. Similarly, T inverse is the inverse of a metric.
okay, for number C, we also just time the matrix again, or do we like say
Yes.
the reasoning?
Yes, if you get this metric, so you just need to multiply x, y. For example, look, you have this one. So if you multiply x comma y, then it will gives you its composition. Like it will gives you the another form of that. For instance, like suppose as I'm telling you that look, if you have this metric, if you multiply T1 or T2, you will get this metric. Now multiply this one minus 1 0 0 minus 1 with x y, then what you will get? You will get like minus x comma minus y.
Oh, okay. Okay, so I understand. Thank you so much.
Yes, yes. So this is actually the just like multiplication in this way, then you will get its proper form. Any other question? Yes, please.
Will the recording of this class be posted on my UNISA?
Yes, exactly. Yes, it will be. It will be.
Thank you.
Yes. So problem number 24. Here is the problem. Yeah, in the problem number 24, it's when you see that if A is any metric, how to find A power n in general form of that. So when you will read the literature on the textbook, then you will get its answer. So for example, A square, you can see what is the A square, what is the A cube. Then you will get its general form like A power 4 will tell us you what is the n, like what how to get or how this will play the general role on that. So just if you apply a square, a cube, a4, then it will tell you that for each value of n, what is the an. You can prescribe it and you can make a general formula for a power n. And the another question, problem number 22 is problem 22. There is no mistake. Look, like uh, so yes, yes, there is a here W1, there is a W2 and W3. You can say about that one. So, and if you run with that one, then still it's fine. Like it will gives you the number as they are repeating over here. So in the both cases you can run. But if you want to change here W1 and then say W2 over here, then it's still fine and you can do it the problem for that. And in that case, hopefully it will becomes here you can say this is W1, the second is W2 and then W3. And here you can just simply that check that it's 1 1 or not. Take a metric A, which is like the metric is 1, 1 minus 2, 1 minus 3, 1, and similarly 1 minus 1, 0, and minus 2. And when you have these coefficients, it's make a metric. Check that this is invertible or not. Like you just take its determinant. If determinant is non-zero, then it means this metric is invertible. So you can apply that thing. So for this, actually, you can since here if W1 or W2, it doesn't affect because for checking the standard metric, it just need to see that behind the metric is this invertible or not. So you need to check the 1 1 of the standard metric. So you can be considered it's W1, W2 or W3, or it will be W1, W1 or W3. So the important thing is that this metric X, matrix A. So you need to see the invertibility of this metric A. Any other question? Yes, please.
Say, on problem 24, are you saying for n, we choose n value that we want? For example, if we say n is 2, then we'll have a squared, then we multiply the two matrices. Is that what you're saying? Or I'm missing something
No.
there?
Someone asks you, I have a number, like what happened when, like if A is a metric, what is the formula for A power n, where A is available and n is any number? And for that formula, it will work. For instance, like it can be a power n is suppose 1 power n, 0, 0, 1, 3 power n, 1 power 2n, minus 1 power n, and 1 power n, 4 power say n. So when you take n equal to 2, then it will make the square of that. When you put n equal to 3, so it means just need to express it into the general formula of that one. And there are various ways to obtain that. The simple is that if you make a square a cube a4, then you will see the behavior of that. Others are the with the when you will see the literature, you can see in the textbook it's also available to figure out that how to find a power n if for any value of n.
Where in the textbook, sir? I did not see it. I tried checking it.
Okay, I will add some topic for that. Okay, for some example, I will highlight or I will explain. Will show you regarding the details of this one. I will share some details. Okay, on the my module website. Okay.
Okay, thank you, sir.
Okay. Okay, students. Have a good day and best wishes. Okay. Goodbye.